So welcome everybody to our first seminar this semester. I welcome Tobias Fritz from University Innsbruck, a speaker of our seminar. He's a frequent guest of our seminar, and he also visits Prague this year. Yeah, so he's a very well-known mathematician among us. 2 years ago, Tobias Fritz gave a talk on categorical probability and the finity theorem. And today he gives completely different talk and approach to homological algebra up to epsilon. Yes, please, Tobias.
Yeah, thanks so much. I'm very happy to be back here. And I guess in the end, the common theme to my previous talk is definitely the category theory. So I guess maybe it's not completely different, since that's the sort of thing that I know.
Yeah, everything connected.
So yeah. So please, if there's any questions at any time, I mean, feel free to speak up and interrupt me, and I'll be happy to just try to answer the questions. So the title, given the title is homological algebra up to epsilon, but actually I realized that maybe a better title, a better name for this would be something more like quantitative homological algebra. So you can, I mean, in the abstract, I think I had used both terms, but by these I kind of just mean the same thing. Okay, but before I talk about this quantitative or what the epsilon means, let me say a little bit about, or given motivation for what's called non-abelian homological algebra. So usually homological algebra takes place in a category, in an abelian category. So oftentimes we have modules over a ring as the objects, right? And then we have exact sequences and things like that. But there are situations where we do not have this kind of structure. In particular, if you look at something like in algebraic topology, the long exact sequence of homotopy groups associated to a vibration, well, there we have a notion of exactness and what long exact sequence means, which may have non-abelian groups and as part of it, since, well, the fundamental groups pi1, these can obviously be non-abelian. So this kind of raises the question, what is and what kind of framework for homological algebra does this fit in, and how can we kind of develop a general theory that contains this as a special case? So yeah, usual homological algebra does not apply, so we need something more general. And before I say more about that, I want to introduce the motivation for my up to epsilon thing. And this comes from a paper by David Kazhdan on what he called epsilon representations. So this is, in a sense, some kind of group theory, maybe geometric group theory thing. And so if you look at here, the abstract and first paragraph of his paper, this is about having a map from the orthogonal group O of n to O of big N. So basically it's talking about a representation of the O of little n, but only an almost representation, in the sense that this map rho does not need to be strictly multiplicative, but only up to some kind of epsilon. And so the question that he answered was, well, can we perturb this almost representation a little bit so as to make it into an actual representation? And this more recently turns out also to be closely related to things like Sophic groups and hyperlinearity of groups and the con-embedding problem that has recently been solved. So just to indicate that this is closely connected to kind of difficult problems that have been of interest to a certain community of people in an operator algebra direction in the last few years. Okay, so but what does this have to do with homological algebra? Well, So the point is that his proof that you can perturb such an almost representation to an actual representation, his proof basically uses cohomological techniques, something that looks like group cohomology. And in particular, so here I've written down on the lower half of the slide, written down the usual differential, or what looks like the usual differential in group cohomology. So we're considering chains that are maps from G to the N into some kind of, let's say, Banach space E, and define the differential as usual. But the problem is that if we don't have an actual representation, but only such an epsilon representation, then this differential is not going to square to 0. It's only going to square to something like, well, operator norm less than or equal to epsilon. So how do we make sense of this, formally speaking? Kazhdan used this kind of structure in order to prove his result. But yeah, so here's his theorem, saying that under certain assumptions on the group, namely for an amenable group, if you have an epsilon representation, and if the epsilon is something like less than 1/100, then you can deform it into an actual representation pi. Yeah, he also proved that this fails for other groups, just to kind of, as an aside, this cannot be expected to hold for all groups. And so yeah, his proof uses this kind of cohomological structure, but it's clearly not homological algebra in the usual sense. And in a way, so one can say his method is successful, but it's an ad hoc method, and that there is no general framework for this kind of thing. There is no definition of what a cohomology group would actually be in his setting.
Tobias, sorry, ask you question. How does this idea compare with, I think?
Sorry, I can't understand you. Yeah.
Sorry, is it too loud?
There's a lot of noise in the connection.
I'm sorry, is it better?
Yes, yeah, much better, yeah.
Okay, sorry, I think my microphone setting was too high. Yes, so these general ideas, how do they compare with what I think some people call persistent homology? If you know about that.
I know, let's say, I know the ideas behind it, but I don't know the technical details. Well, I think persistent homology, I mean, uses ordinary homological algebra and well, homology and applies it in a context where we look at things up to epsilon. But I would say this is very different in the sense that here we do not have we cannot use ordinary homological algebra.
I think in persistent homology, the epsilon is a formal variable. So like it could square to 0, right, for example, or cut off at some higher power.
Okay, but you still yeah, have actual chain, normal, right, I mean, chain complexes in the usual sense, right?
Okay, and here you have a more analytical
Here flavor. We do not.
Yeah. Okay, all right, thank you.
Yeah, sure, you're welcome. So when we had started out working on, I mean, I was working on this with someone who had kind of proposed this to me, and initially we had actually tried to do something like that, a persistent version of group cohomology, but in the end and that may exist, but in the end it somehow didn't work out, and it's unclear if one can use it to do what Kazhdan did. Okay, yeah, so we need something other than the usual homological algebra. And as I had said in the beginning about the nonabelian homological algebra, this is something this kind of problem is something that people have thought about quite a lot. And there's various approaches to how one can generalize abelian categories to things called homological categories and things like that, where one can still where one still has, to some extent, ordinary homological algebra, things like the snake lemma, the 9 lemma, and so on. One can make sense of long exact sequences. And one such framework, and it's not the only one, but it's one of them, is by Marco Grandis, coming from this book that I've displayed here at the bottom. And his framework seems somehow, at least to my mind, very natural, and it seems that one can apply it to the epsilon homological algebra problem. And that's sort of what I want to talk about for the moment. So yeah, let me forget about the epsilon stuff for the moment, and just introduce the basic setting of his framework. So what he starts with is any category C together with a subset, a collection of morphisms that are considered the null morphisms in the category. So in the abelian case, of course, those would be the zero morphisms. In the category of groups, it would similarly be the trivial homomorphisms that map everything to the neutral element of a group. And in general, it's just required to be an ideal of morphisms. So if you have any null morphism and you compose it with any other not necessarily null morphism, you still get a null morphism. And so like this, we can still define what a kernel is. And so this I've displayed here in this diagram. If we have a morphism f from x to y, then the kernel is any morphism into x, which has the property that when we compose it with f, we get a null morphism. And such that if we have any other morphism g into x, such that f composed g is a null morphism, then this g should uniquely factor through the kernel. So this is the definition. It's it's just the usual definition, just adopted to this more general setting where instead of having zero morphisms, we have these null morphisms. And yeah, cokernel then of course is defined dually. And it's a little surprising that if we only assume that these kernels and cokernels exist, that this is enough to prove quite a number of things already. So for example, we can just based on this setting show that every kernel is the kernel of its cokernel. We can introduce something called normal subobjects. So a normal subobject of an object X is basically just a kernel, a morphism into X that is the kernel of some morphism out of X. And then just based on this one can prove that these normal subobjects form a lattice. So in particular, we can take intersections of subobjects, and we can take unions of subobjects. And there's a largest and a smallest element given by, well, the identity, unsurprisingly, is the top element, and the kernel of the identity is the bottom element.
Sorry, are you assuming some direct sums or push-outs, pullbacks to exist?
No. That is the surprising thing about this, so direct sums would require, I guess, an additive structure to begin with. So, but we don't even have an additive structure in this category necessarily. Yeah, I mean, if anyone is interested, I can say a bit more about how to construct, for example, these intersections of subobjects or this kind of thing. And so these are called normal subobjects because it's somehow modeled after the category of groups, where these normal subobjects then are the normal subgroups.
I also wanted to ask you, like, your null morphisms, you don't ask for a null object to exist?
No, exactly. So actually in Grandis' book, he assumes that kind of thing in a slightly weaker sense. So he often assumes that every null morphism factors through an object whose identity is a null morphism. But for the epsilon homological algebra setting or problem, I don't want to assume that because that's not the case there. But yes, it's definitely an interesting and relevant condition for some things. Okay, so yeah, although one can do quite a bit with this kind of structure already, it's, I guess, unsurprisingly not enough to do any kind of non-trivial homological algebra, like proving the snake lemma, this kind of thing. So in order to do that, we need additional axioms. And I don't want to write these down now, but so yeah, Grandis has axioms that achieve that, and then he calls those categories which satisfy these additional axioms homological categories. And then he's proved quite a lot of, developed a lot of homological algebra, snake lemma, long sequences, spectral sequences. That is basically, so basically all the usual stuff. So as interesting examples, we can take, maybe let's start with the category of groups. The category of groups is unfortunately not homological. And the reason that it fails is because he requires basically kernels to be closed under composition. So if you have a morphism, that if you have two composable morphisms that both are kernels of another morphism, then the composition should again be that, but that fails for groups because that would mean that inclusion of normal subgroups would have to be transitive, but that's not the case. When you have a normal subgroup of a normal subgroup, it's not necessarily normal in the larger group. But an example that satisfies it, and this is maybe a little bit more obscure, would be the category of lattices as objects, and Galois connections, meaning auto-preserving maps that have adjoints as morphisms. And here, this would be an example where we can also see clearly the Hom sets do not have much of an additive structure. Okay, now let me get to the epsilon setting again. So I'm going to fix, as in persistent homology, let's fix the epsilon. And here it's important that epsilon should not be a formal variable, but an actual number. And then I want to define a category with non-morphisms, where I just take the objects to be real vector spaces equipped with a semi-norm. The reason that I only postulate a semi-norm, meaning that I allow the norm to be 0 on non-zero vectors, is just mainly a matter of convenience. We're going to see later in the construction of cokernels, if instead of semi-norm I would require a norm, the construction of cokernels would be pretty ugly. And using semi-norms, we got an equivalent category with a nicer description of cokernels. But so just to indicate that postulating a semi-norm here is kind of conventional. Okay, and I want to take the morphisms to be linear maps of operator norm at most 1, and where I identify any two of them if they differ by a map of norm 0. So if they differ by an f, that lands completely in the null space. And now if we go back to Kazhdan's cohomology, or supposed to be cohomology, his d squared, the ideal is now to say that, well, his d squared should be a null morphism. And so in his setting, we would like to say that, well, all morphisms that have norm at most epsilon, those are basically 0. So those play the role of the null morphisms. And that's why then I'm defining the null ideal as the set of all morphisms that have a norm of at most epsilon. And now it's obvious that it's an ideal because all morphisms I require a norm at most 1 anyway, and since the norm operator norm is submultiplicative, that shows that we have that the ideal is closed under composition by arbitrary morphisms. Okay, so this is the category that I want to work with, and indeed it turns out that this satisfies these, the conditions here. It's like kernels and cokernels in this category exist. And now I want to try and describe a little bit what these kernels and cokernels are, because yeah, I think this is quite interesting to kind of get some understanding of what changes if we throw in this epsilon. So the kernel of a morphism F turns out to be just the same. We can take just the same vector space X again and only change the norm. Yeah, and what the norm is just the one that is written down here. And to understand this, think about the case where f of x is, let's say f of x is small. That would be the case where we would want to say, in that case, x is kinda in the kernel. And in that case, this new norm is going to end up, well, no, sorry, now I'm getting a little confused myself. So yeah, these things can be.
Yeah, I also get confused because the kernel here is some real number.
No,
And
the kernel is the vector space X itself,
yes.
equipped with a different norm.
Yeah, yes. Okay, I understood. Yes, so that's yeah.
And so the idea is that if we look at an X that has a large norm, in that case, it is, roughly speaking, outside of the kernel. Because X then having a large norm would mean that it's the second part on the right-hand side that dominates. And that, intuitively speaking, means that the norm of f of x itself is not particularly small. Whereas if we have an x where the norm on the left-hand side is small, then that means that the norm of f of x itself must have been sort of small. And in particular, less than or equal to epsilon times the norm of x. And so in this sense, one can say, yeah, this is in a sense a quantitative version of what a kernel of a linear map is. The kernel is no longer a subspace, but it's this kind of more quantitative thing of, roughly speaking, this a norm that measures how close X actually is to being in the kernel. This is some kind of vague intuition behind it. A little easier to understand is maybe actually to write it in terms of the unit ball rather than the norm. If you just translate this max into what it means for the unit ball, then the unit ball of the new norm is precisely the unit ball of the old one, intersection with epsilon times now the usual the pre-image of the unit ball in Y. Yes, that's right. Yeah. Okay, so these are the kernels. And cokernels, if you know, are also kind of similar in spirit to the kernels. But in this case, we take the codomain vector space and equip that one with a different norm. And this new norm looks a lot like a quotient norm. And if you study quotients of Banach spaces, right, then it's basically this sort of infimum like they are on the right-hand side, just without the second term, namely with epsilon being 0. So if you take epsilon equal to 0, then this is actually the quotient norm. This is y modulo the closure of the image of f. But now with this epsilon, it's something a little different. And again, one is supposed to think of this in some kind of quantitative sense, as in this norm itself somehow is a quantitative replacement of just the vector space, the quotient vector space. And yeah, the new unit ball looks like this, as this kind of convex hull. Well, modulo including boundary points, but it's essentially this.
Tobias, I think there's a question in the chat.
Oh, okay. Should this be inf over x and x? Yes, thanks. Yeah, that was a typo from a previous notation I had used using V. Yeah.
I wanted to ask you, for the time being, your choice of a seminorm does not play a role, right? So, like, if now I use this new norm you've defined and just factor all the things that are that have norm 0, I will still get like an isomorphism, so still a cokernel, right?
Right. So you mean if this is well defined with respect to equivalence of morphisms?
Yes. If we can move from seminorms to norms for these notions of kernel and cokernel.
Oh, I see. So for the kernel, yes, but for the cokernel, no. The problem being that, and this is exactly why I'm using seminorm at a technical level. If we were to work with norms, then this could be 0 for some non-zero y, right? And in that case, we would have to explicitly take a quotient in order to get a norm again, rather than just a semi-norm. But so the cokernel semi-norm has a nicer form if we work with semi-norms. But actually, as categories of null morphisms, the two choices result in equivalent categories, so it doesn't actually matter. And in this sense, it's only for convenience. And I think it's kind of nicer to say that, well, the kernel just replaces the norm on X, and the cokernel replaces the norm on Y, but otherwise, in both cases, the spaces stay the same. Okay, so to get a little bit more in a homological direction, let me talk a bit about exactness. So in a general framework of these categories of null morphisms, we can say that a composable pair, and take this definition, is exact if the composite is null, and if the kernel of the second, well, is the image of the first one, and image is just defined as the kernel of the cokernel of F. So this is a normal subobject of Y, and the condition is just that these two normal subobjects should be the same. You can also phrase this, and I mean, dually in terms of the cokernel of F should be equal to what's called a co-image of G. But yeah, that is equivalent, and written in this form, I guess it's more like the usual element-based definition of exactness, and so that's why I've written it like this. So yeah, and if you then work it out, what this amounts to in my category norm epsilon, it ends up looking like this. And yeah, I don't want to say very much about this inequality other than saying that we can kind of interpret this in terms of boundary and cycle roughly. So if we think of the image of F, I mean, the image of F, I just want to call this the boundaries and the kernel elements that are in the kernel of G. I want to call these the cycles and just use this kind of terminology to explain things intuitively. And so then what this is saying, this inequality at the bottom, is that in a sense the left-hand side measures how far an element Y is from being a boundary, because when this thing is large, or no, so yeah, let's say when the left-hand side is small, that means that there is an X such that F of X is close to Y, and also the norm of X is not too large. So that kind of maybe justifies saying that, well, Y is kind of is close to being a boundary in a quantitative sense. And the right-hand side measures how far Y is from being a cycle, because here we're kind of comparing, yeah, I mean, here we're looking at the norm of G of Y. And that's how I think about this inequality here. Okay, so yeah, but ultimately the goal was to kind of try and make sense of Kazhdan's cohomological considerations. And for now, this, yeah, unfortunately has not been achieved yet, but I think it should be doable. Or at least I'm hopeful that this is a good framework in order to achieve that. And the evidence that I have is that if we compare this definition of exactness that I've just repeated here in the box with Kazhdan's ad hoc definition, it looks somewhat similar. So in a quantitative sense, I mean, the maximum on the right-hand side coincides with the sum of the two terms up to a factor of 2, right? We can bound one in terms of the other up to a factor of 2. And also the left-hand side is vaguely similar, at least. and so that's kind of why I'm hoping that my notion of exactness that comes out as an instance of Grandis's framework could be used for the same purpose as Kazhdan's explicit ad hoc version. Okay, but now I kind of want to get to the second part, namely that there is a problem with doing homological algebra in this category norm epsilon. So as I said, Grandis has these additional axioms that result in a definition of homological category. And my norm epsilon is not a homological category, no matter what the value of epsilon is. And the problem is exactly the one that I think Antonio had asked about earlier, that Grandis requires every null morphism to factor through a null identity morphism. And that is just not the case because there are no, well, okay, the zero vector space has a null identity morphism, but that's pretty much the only one. So this is just not the case in this category. So then the question is, well, what can we do about cases where Grandis's axioms do not hold? And already Grandis, if you look at Grandis's book, he already deals with this kind of issue a lot. And he deals with it in a way that is also kind of very classical in algebraic topology, namely to work with pairs. Let's say pairs of spaces play an important role in algebraic topology, right? And this turns out to be true very generally. And so then what the other thing that I showed is that if you only assume kernels and cokernels for the category with null morphisms, then its arrow category always satisfies Grandis's axioms. It's always a homological category. And so we can always work in the arrow category. And so this is kind of now what I'm hoping here, although I mean, it hasn't been worked out yet in the application to Kazhdan's problem, that if norm epsilon does not turn out to work, then one can still use the arrow category. And so, yeah, let me indicate what happens when one uses the arrow category. And I kind of want to argue that using the arrow category is somewhat interesting already in the case, the standard case of abelian categories and doing homological algebra in abelian categories. And to illustrate that, let's just see what happens when we construct a long exact sequence. So as the starting point for a long exact sequence, I mean, we typically have a short exact sequence of chain complexes, right?
So now you consider usual chain complex d squared equals 0.
D squared being a null morphism. So
So that's
yeah,
the chain complex associated with the norm epsilon. So that, yeah.
This is still this is still in a general framework of these categories with null morphisms, and the assumption is just that d squared is a null morphism. Yeah, so then since the arrow category is a homological category, one can apply Grandis' result to that arrow category and obtain a long exact sequence of homology objects that now live in the arrow category. And so now this is maybe a little complicated, but here's what this long exact sequence looks like. And you should think of these, so the vertical arrows are the homology objects. So this, I mean, I'm drawing this as a diagram in C, and so the homology objects are arrows, and it's precisely the vertical arrows here. And if you look at the middle vertical arrow in particular, this is the vertical arrow that goes from the kernel, basically the object of cycles, to the cokernel of the previous differential. And so this cokernel you can think of as chains modulo boundaries, right? So the sort of homology object that we get in the arrow category is a canonical map that maps us from cycles to chains modulo boundaries. And the other homology objects are kind of similar to that. They also then kind of involve these inclusions, so this has a bit more of a relative flavor. I can try to say a little bit more about this if anyone wants to know, but maybe it's a little too complicated for just a talk like this, so I think I'll move on for now.
What do you mean? What do you mean by double diagonal is null?
Right. So this is just translating the fact that in an exact sequence, in particular, composing any two arrows results in zero or now a null morphism. And the null morphisms in the arrow category are those squares that have null diagonal. Okay, I see. Thanks. So here what I mean by double diagonal is just that we take the diagonal of two squares or of a composite square. And that's what that's what it means to say that in this long exact sequence, the composite of two morphisms is null. Yeah, I was maybe being a little sloppy when I said that this is a long exact sequence. It's actually not necessarily, and this is a bit maybe a bit of an ugly aspect of this, that its exactness requires additional modularity conditions that again were worked out by Grandis. And that unfortunately makes it a bit difficult to apply. But yeah, that's how it is. Okay, now let me specialize to the abelian case, and just to indicate what one gets in that case. And as I had indicated by the talk about elements, on top we have kind of objects of cycles. At the bottom we have objects of chains modulo boundaries. So we got the usual homology if we take the image of this canonical map that takes us from cycles to chains modulo boundaries, right? Because homology is cycles modulo boundaries. So when we draw these images, and then of course we get induced arrows between these, then we get the usual exact sequence. In the abelian case, we got a usual exact sequence in the middle of this thing. And so that's why I think it's kind of somewhat interesting, and maybe already in the abelian case, and it gives a fresh look at how long exact sequences arise. Yeah, I don't think, I mean, maybe one might even think that the exactness of this thing in the abelian case would be a stronger statement than the exactness of the sequence of images here in the middle, but I think that's not the case. So the exactness of this thing is just equivalent to the exactness of the long exact homology sequence. Okay, so now I'm already kind of nearing the end. And I don't have anything to say at the moment about applying this now back to the epsilon setting, or to the norm epsilon category. But I can illustrate it maybe a little bit more with the category of groups and see what these, so that one can get a bit of a better idea perhaps of what these long exact sequences, what they look like. So yeah, here's just an example of a short exact sequence of chain complexes. The first one, well, is 0 except in 1 degree, where there's just a subgroup H of some bigger, a normal subgroup H of some bigger group G. And then let's say we have also a normal subgroup K of H, but let's just choose such a K is not a normal subgroup of G. That's going to be the case where the usual naive approach would fail, but the arrow categories approach works. Yeah, so if we could use the usual exact sequence, then it would basically end up looking like this. So here, this first K on the left, this would be the homology object of the K in the bottom row, right? And then we would have the connecting homomorphism to the homology object in the next degree of the top row, which is just H. And then we would get, here in the middle of this, G modulo K. But now, since K is not normal in G, well, what this G modulo K should mean is that G modulo the normal subgroup generated by K. And so that's what I mean by these square, by these brackets. And yeah, then this is what it would look like. But, well, this is not exact, of course, at H. Because the map from H to G modulo normal subgroup generated by K, well, the kernel is the normal subgroup generated by the K and not K. So here the exactness fails. But if we set this up as a long exact sequence in the arrow category, then this is exact in the appropriate sense. And at least here at a formal level, now this has kind of fixed the problem. It's still a bit of a bit weird in the sense that, I mean, of course, we're not fixing the discrepancy between K and the normal subgroup generated by K, and that is still there. The difference is somehow just we're changing the definition of what exact means, and now we got a long exact sequence. Okay, yeah, then I'm basically also kind of at the end already of what I had wanted to present. I hope it's been somewhat meaningful and possible to follow. So let me just summarize and also to indicate what the status of these ideas is. So the original motivation was to note that Kazhdan's cohomologically flavored techniques, they kind of hint that there should be something like homological algebra up to epsilon, or some sort of quantitative homological algebra, where differentials do not need to square to 0. And yeah, this in order to address that, I've been proposing this category norm epsilon, and I think of it as some kind of quantitative homological algebra, and quantitative in the sense that it has some kind of, if you look at this formation of kernels and cokernels, has some kind of inherent fuzziness in the sense that the cokernels and cokernels, yeah, a kernel is not a subspace anymore. It's the same space equipped with a different norm that measures something like how far a morphism is from mapping to 0. And this does not, so being in the kernel is not a yes or no thing anymore. That's actually essentially what I want to say. And yeah, it seems plausible that working with this category can reproduce Kazhdan's considerations as part of a general framework. But on the other hand, it just lacks one of Grandis's axioms, that would make homological algebra well behaved in general. I'm not actually sure how important this axiom is in his framework. It's possible that it's largely dispensable, in which case there would be no need to move to arrow categories. But it's also possible that it's really important, and in these kind of situations one can still, so this was then kind of my second point or my second theme, one can still move to the arrow category in order to get a homological category in Grandis' sense and apply his results. And yeah, I think this could be an interesting strategy in general, maybe. And what one obtains like this is that the homology objects, instead of them being actual quotient objects, they become arrows. And one can think of those arrows as the arrows from cycles to chains modulo boundaries. And yeah, I try to illustrate that with an example involving non-abelian groups. Okay, so yeah, that's basically what I had wanted to say. And yeah, thanks for listening.
Yes, thank you very much, Tobias. Yeah, yes, completely new approach, but still it's a lot of open question, right? That so that's at the moment you don't have any applications. That mean related new approach to some reason or
no, there's no other. I mean, the application that I would hope to get is just Kazhdan's.
Kazhdan result.
To first of all reproduce his result,
Yeah.
and then kind of try to do more things along those lines and put the Grandis' machinery to work on similar problems like Kazhdan's. But yeah, that is open, and yeah, I don't have any. So in other words, I don't actually have any applications so far. Yeah.
So I also do not understand the last year example on the sequence of the norm. How to say? Subsequently, it can extend to normal subgroup, but it's a not normal group. Of course, I also think about this example and I consider covering space when it's a regular and infinite. Yeah, but can you that is your example or the Grandis example?
No, that's my example. So Grandis had considered categories of pairs.
Yes.
But using arrow categories, he hasn't considered arrow categories.
So it's the example of the so he proposed to consider category of pair and you propose to consider category of arrows.
Yes, and I think these arrow category, working with arrow categories is simple. It works very generally.
Yes.
And Grandis' results in categories of pairs seem a little bit more convoluted.
Yes. So in this example, can you get some new reason if is in geometry? For example, I try. Of course, not every covering space can be how to say written in that way. That's composing of the regular covering, but even it's that setting also interesting. That is geometry picture I have in my mind recently. In algebra, there's any possible application either on geometry or algebra? Do you have?
That's good question, but that's that's difficult for me to say because I don't think I have enough of a background idea how what that could be. But of course, in that, as a first thought, I would think that it's unlikely because if that was possible, then people already would have found or been able to prove the result using more direct methods. So yeah, my belief is that more like the first applications are more likely to be in some kind of more like functional analysis setting where one has really where there's something like this, the differential actually not being zero would be important, where that could be used.
Okay, is there more some questions?
Yeah. So if you can hear me well.
Yes, yeah.
Yeah. I'm just wondering, like, what would be your approach to reproducing the result of something like Kazhdan's result? Like, are you hoping for something like a general, like, implicit function theorem or a fixed point theorem that will, like, reduce the epsilon picture to like epsilon equals 0, which would reproduce standard homological objects?
Yeah, I mean, assuming that my proposal works, I think the proof of or reproving Kazhdan's result, that the proof would not be substantially different, but it would just sort of spit out that proof as part of a general framework. But or let's say at least the cohomological part of the proof. And what he actually did is exactly what you suggested, almost in that he kind of constructs an epsilon prime representation for a smaller for an epsilon prime that is something like 5 times epsilon squared or whatever, so somehow smaller than epsilon, and then iterates that and uses compactness argument to show that you can get to epsilon equals 0. And I don't think I mean I can replace that. That's not the cohomological part of the argument.
So I guess if you have a general result like that, then any problem that can be formulated as you know, having d squared equals 0, you could try to prove existence of that, like starting from an approximate setting, and then try to show that, okay, in the neighborhood you have an exact one.
That's yes, that's an interesting point. Yeah.
I guess anything that can be formulated as a Maurer-Cartan equation could maybe fit into that
the
framework.
curvature. How is that? Oh, I mean in terms of curvature bounds or something that you can.
Well, I mean, Maurer-Cartan equation is just like it's a representation for any kind of nonlinear equation where you pack the nonlinearity into a you write it as a linear and a quadratic term, and then you pack all the nonlinearities into the quadratic term.
Oh, I see. Okay, that's a more general.
And then
okay.
you know, if it's overdetermined, you have extra differentials that tell you about the degeneracies in the equations and so on. So it just seems like yeah, a lot of problems could be fit into that framework. So if you have some implicit function result or existence result, I think that would be great.
Well, sorry, what is the relation to implicit functions? Implicit function theorem?
Well, so if you're trying to solve the equation d squared equals 0, that's an equation on d.
Okay.
But if you start with, you know, some approximate solutions, so d squared equals epsilon, like some neighborhood of in the space of differentials, and it's exactly what you have here. And so if you can prove that when d squared is less than epsilon, that there must exist a d squared in that space of differentials, then that's an implicit function theorem. At least that's what I would call it.
Okay. Yeah, that's a very nice idea. Yeah, thanks a lot. Yeah.
Okay. All right. Thanks.
Is there more any questions? So if there are no more questions, let us thank the speaker again. Yeah.